Good morning all. Today we will be discussing about Turing machine. It is a topic from automata, that is automata theory and formal languages. So before going through Turing machine, we already have learned some of the topics, like we have already discussed about finite automata, we have already discussed about PDA and LBA. Now if we check the hierarchy of the grammar, we will be having it. We have already studied this diagram before, the around the first lecture of the our series, where we have studied that the most complex grammar, or that grammar is called type 3 grammar, that is regular grammar or regular language, that we have studied with finite automata. These grammars are accepted by finite automata, and we have seen that finite automata is a theoretical machine where we don't have any kind of memories, and we have seen that any grammar where we don't need to calculate any specific numbers, like any a to the power 3, b to the power 3, suppose even up to ax, bx, where we don't need to be infinite number of countings, where these are the languages that can be accepted by this finite automata, accepted or rejected by finite automata. Then we have studied next grammar, that is type 2 grammar, which is context finite CFG context free grammar, where we have studied this context free grammar, and we have studied PDA related to this, where we have used a machine plus a stack, where we have seen that certain machines now it can have a limited, it can do some calculation, that can be any calculation that can be done by a stack, can be those problems can be solved by PDA, where we have seen that a to the power and b to the power n. Now because we have only two calculations, like we can insert all the a's to a stack, suppose 3a, and then if we discard this 3a at the end, there will be only stack, that is stack top. This kind of examples we have seen in PDA, that this can be solved by PDA. Then there come some certain examples, like a to the power n, b to the power n, c to the power n. Now we have to calculate, like a number of a is equal to number of b is equal to number of c's. And now this kind of problems, or WW, where a string repeated by its the same string, that is 101 suppose and 101 again. So this type of strings cannot be determined by PDA. Then we have studied again a small portion, that is type 1 grammar, that is context sensitive grammar, and these grammars are accepted by LBA, where we have studied a LBA is, we can say it as a special types of Turing machine, where the input length, tap length is equal to the input size of the input, and it will be always bounded by restricted by some n markers. And suppose our input is a b b, so our tap length will be only restricted to up to a b b, and we cannot increase its length. So that this is the restriction in LBA. And finally we will be studying today as type 0 grammars, which is accepted by Turing machine. These are recursive enumerable languages, or recursive enumerable grammars, where we will study this topic. So in this topic, aim of this session is we will provide a complete understanding of Turing machine here, and then these are the instructional objectives and learning outcomes. By end of this session, we will be able to define what is Turing machine. We will see some of the Turing machine examples. We will see operations of the Turing machine and how it simulates any behavior of computational tasks, etc. will be seeing here in these examples. Now Turing machine, this is just now what I have explained, like in regular language, whenever there is no need of counting, that is no equal number or nothing, that kind of examples we can solve by finite automata. Finite automata in the sense whether it is DFA, NFA, or Moore machine or Mealy machine. After that we have seen there are certain examples that cannot be resolved with this finite automata. Then we went for PDA, and then after PDA we have studied Turing, and now we will be studying Turing machine, where we will see there are certain examples like A and B and C n or WW, this kind of strings can be accepted by Turing machine. One thing you can notice here, it is a sad diagram actually, if we see here, now the bigger set that is the outer layer, where we can see that that regular language is a subset of like a context free languages, where we have this we already know that any regular languages can be termed as this can be solved by PDA also. Again, PDA has certain advantages. Similarly, all the languages that are solved by up to PDA or LBA can be solved by Turing machine also, they are accepted by Turing machine as well. With this, Turing machine has some more advantages. That's why Turing machine has is the bigger set compared to context free language or regular language. All these are subset of Turing machine, like a proper subset of Turing machine. Now this is a basic diagram of Turing machine, where you can see that in Turing machine we will be having a system, that is a diagram that you can imagine similar to a DFA, where we have some states with transitions to moving from one to another, and then we will be having a added advantage, that is the infinite tab, where you can store our input and we can do some operation that we will see in this lecture. This tab and this stack will be locating to any of the cell of this infinite tab. This is infinite, like you can go to any of this direction. Basically, after input, all this part will be correspond with the black symbol, and whenever we will be using this, we can extend to the right or left hand side. That is, there is no boundaries. And this any of the state at any point of time, any of the state from this diagram will be pointing to one of the cell. And basically we imagine that this is our starting location after that our first state should locate to this cell, that is the first cell. Now this is after this, at each point of time our Turing machine will be working in 3 steps. That is, it will read a symbol from the input tab. Suppose it can read a symbol from the tab, that is A. It can write it, like either it can replace it or it can keep as it is, and then it can our state, whatever the current state was, it can move to, it can change to another state, and it can move to left or right direction. So suppose here is an example. In our tab we have A, B, A, C. So first we are reading a symbol from the tab, that is A, that is shown by the arrow, that we are reading this symbol. Then what we are doing, we are writing it by K, that is we are replacing it by K here, and then we are moving to left direction. If we now move to right direction, now suppose in this example, here we are we are pointing to this, suppose any state we have, and we are pointing to the B symbol B. Here what we have done, here this B is replaced by F, symbol F, that is we are in place of B, we are writing F here, and we are moving to right direction, that is one bit this side, that is here. Now our read write head is pointing to this symbol, that is under the read write head we have the symbol K. So this is our input string. Input string is always bounded by some blank symbols. These are the blank symbols. You can write any symbol like B or this symbol, or in some book you will be finding this symbol. But remember that this blank symbol cannot be a part of your input symbol. If you have any symbol in your input as B, then that cannot be, you cannot write here. Or if you have this symbol as a part of your this input output symbol, then you cannot write it, consider it as a blank symbol as well. Now any state, and this is an example of state and transition. This transition says that on Q1 we are reading an input symbol A, we are replacing it by B, and we are moving to left hand side, and the new state is Q2. And the second example is on Q1 we are reading input symbol A, where we are replacing it by B, and we are moving to the right hand side. So we will be using this terminology A, then B and L, and the new state is Q2. So this is our timestamp. Suppose so here our input current state is q1, it is reading a, then here we are writing it by b, so we can remove it by b, and then we are going to right hand side here, then we are going to right hand side here, and so right hand side is this side. Now our next state like should be here q2. So you can see here a b a c, after a replace it by b, and we have moved to this symbol q, under the read write has a c, and now our new state is q2. So this was our initial state, after the timestamp we have in this state. Similarly this one in left hand side, once with the left operation, what we are doing, we are currently in q1, we are reading the symbol a, we are replacing it by b, and we are moving to left hand side. Similarly this one, in this one our read write head is having a blank symbol, so what we are doing, we are replacing it by g, so we are having a g here, and we are moving to right hand side, that means this location, and our new state is q2. So Turing machine is like what are allowed in Turing machine, and like that is Turing machine is deterministic in the sense of inputs. Input means like with a current any symbol, a particular symbol on a state, like this is our suppose, so this with this input we can go to any particular one like a state only, or we can change it by only one symbol at a time. We cannot have this non-determinism, like a can be replaced by either b or d and move to right or left. We cannot have this one. Only when we have studied our DFA, that time also we have seen in DFA by reading a input symbol we can move to only one state. We are not allowed to move to more than one state. But in DFA we have also seen that suppose our input alphabet is A to A and B, suppose that we have to mandatorily give a transition for B as well. Even from the final state, if there is no transition, then we have seen that we have like made a dummy state, and we have given all the transition for A and B. But in Turing machine we don't need to do that. We have to only give the transition for those states which are like mandatory, like which in our diagram or according to our problem we have to give. Other we can ignore, but we have to remember only one thing, that is by reading only a symbol we have to go to only one state, like we can only do one transition, not more than one transition is allowed. But in particular a state, suppose from a state with two different symbol, we can write more than one transition also, because these are like different symbols, so these are allowed. Only with reading the same symbol, this part is not allowed in Turing machine. Also partial transition function is allowed. As I said, in determinist, in DFA what we have to do is, in DFA we have to give all the transitions related to per state related to inputs. But in Turing machine we don't need to give all the transitions. Suppose here in our input tab we have A, B, A and C. So from Q1 we have, this is a Turing machine with Q1, Q2 and Q3 states, where we have seen from Q1 we can go by reading A or by reading B. There is no like states given corresponding to, like no transitions given corresponding to this symbol, in this input symbol C. So this is allowed. You can give on, you are like, if you don't need in your diagram, then that is not mandatory, you have to give. So next term is halting. What is halting? Halting means the machine halts if there are no like possible moves after, or possible transitions to follow further. Suppose somehow we have reached to up to A, then while reading C, now suppose we are having here this transition Q2 to C, but we don't have written any transition in this diagram, so we can say that now our Turing machine halts after reading this symbol. Now where it halts, it is an important like point in Turing machine. Suppose here the same example, like we have seen that it is halting. Now if your like after coming to final state, if your Turing machine is halting, that means it is allowed. That is like, okay, now this is not the same example. Anyway, in the after, if your Turing machine halts in your final state, that is if acceptance of input means if it halts in the final state, that means it is allowed. otherwise it is rejected. Means if your machine is halting in a non-final state, or if your machine enters to an infinite loop, then it rejects. We will see these examples in like following slides. Now in final state, again in related to DFA, we can see from in DFA we have seen that from final state also, like we can move to further states, that is allowed in DFA. But in Turing machine, we have to remember this one important topic is that final state can be considered as we have to consider it as the final state. Means there are no more states can be allowed to, like no more transitions are allowed after the final state. That means final state have no outgoing transitions. Now this is an example of Turing machine. This is also an example of like the same thing you can imagine as a DFA. In DFA, what we seen, A star. A star means if we consider the language, that means there can be epsilon, there can be A, then followed by AA and any number of A. That means our initial state is the final state, and we will be having a loop in DFA. If we design a PDA for the same example, so we will be having the same thing actually, but in our PDA we will not do any operation. Only if any number of A comes and our stack top is Z0, what we will do, A will not keep anything, we will just keep the Z0 as it is. When our input symbol ends, then if our input has nothing and Z0, that means it is Z0 and it is the final state. That is the PDA diagram corresponding to this input. Now in Turing machine, what we have to we have is any A star, that means any number of A. So our input, if we take any input from this, suppose A and then followed by blank symbol. So this is suppose our input tab, and our current state, that is the initial state, that is Q0. So Q0 is locating to it is pointing to the first input. So what we have to do is any number of A comes, then we have to accept it, and once it all the A we studied all the A, after that we have to we can say that there is only A, that's why we can accept it. That means we don't need to replace anything. So what we are doing here, by reading A, what we are doing, we are just keeping it back, that just we are moving to next symbol. Then again A, if we got, again if we get another A, we will be going to this. Finally if we get a blank symbol other than any other symbol, then we can say we can move to any direction, either left or right, and finally we will be going to the final state, and this is our acceptance state, and this is the diagram for this. Now look at this example. That is the same string, that is AAA. So we can see here, after all the A, it is going to throw the self loop, and then on this it is going to Q1, that is the final state, and this accepts. Now with this input on Q0 we are reading A, so we are going to right hand side, so we have done with this. Now once we go to B, now no move is written in Q0 with respect to B. That means it is halting in Q0, and it is a non-final state, so it will reject the input and halt. That means our Turing machine up to this is correctly designed, just this current input is not considered for this machine, so it is rejecting the input. Now suppose a example of infinite loop. Of course this Turing machine is wrongly designed, because our input symbol, you can see that it is a AA star. That means at least one A should be there, followed by n number of A's, or B followed by any A or B symbol. We can check from this input. So this is the correct Turing machine. But if we have wrongly designed, we can see here after a certain point of time, like A, B, A, then we have a transition. After B we are going to left direction, and again what we are having, we are again having A. Again if we are going in another time stamp, we can see again we are in a loop. Actually it is a never ending loop, because once we are going to this, again we are coming back to this, again we are going to this and coming back to this, and it is still Q0 state. We are never going to Q1 state. So it is an example of infinite loop. So we have to, like, any machine cannot have an infinite loop. If any machine is having infinite loop, means there is again we'll be facing some problem, right? Suppose we imagine a ticket booking counter. if you went for booking a ticket, and if you find that there can be three kinds of situation always. First situation is ticket is available, so you are given some ticket and you can leave. Another one is the person said there is no ticket, so you can leave. That is another, like you have said yes or no. That is, now someone said you wait for a time, sometime we'll check and come back. Now this sometime can be 5 minutes, can be 10 minutes, can be never ending. So it is actually infinite loop. We don't know when this time will come. Similarly, we have seen in our C programs also, if we suppose we have given for loop wrongly, then this program enters in one of the simplest example from C program is it goes to infinite loop. So we cannot determine whether our input is correct or not, or program is correct or not. So this type of situation must be avoided, and in Turing machine we say that if something is entering to the infinite loop, then it should be rejected. So we have seen in this example that because of infinite loop, this final state can never be reached. So machine never halts. Actually, it is moving to in the same state with that infinite symbol, that is left and right, left, right, in this way. So the input is never accepted. Now we can see this another example, A and B n. So how to design this Turing machine? First let me discuss with you. Suppose now our state is A and B n. We have seen this is accepted by PDA, but this type of input cannot be designed by this type of machine cannot be designed for finite automata. Now in case of Turing machine, how to design this machine? Imagine, like what we have to do basically here is we have to calculate number of A's and number of B's. Suppose we have an input, suppose something we are writing here, suppose A, B, 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 followed by blank symbol and blank symbol, suppose. So if it is a number of equal number of A and B, then our machine should accept it, other than the conditions, like if we have 2A and 3B, that also our machine should reject. Similarly, if we have A, B, B, that also our machine should reject. So what we will do here is, in Turing machine concept, what we do is basically we use first A. Suppose we start with this initial state, we replace it by a symbol, and then we will move to first B and we will replace it by another symbol. If we replace it by same symbol, later we can we will be in a problem, it will be accepted, it will accept this string as well if we replace it by same symbol. So to remember that we have now checked for one A and correspondingly one B will be checked. So we will replace it by another symbol and we will go to this. Again up to this is one iteration you can imagine. So Q1, Q0 we are starting doing something, and again we will be back after reading this X, we will go to this one. So we will replace it by X, and this side we will go up to ignoring everything. Whenever we will see the first B, we will replace it Y, and again we will go to the left direction up to our first X. Whenever we have seen our first X, that means we have replaced this by A, and then we can go further. So after this one we will again, we have this A, so we will replace it by X, we will go to this side and we will replace it by Y. Now once we replace this, if we go back to this side, now after X we have to turn this side, but there is no A. So what we will do, we will further check, that means all the A's are completed. Now we will check up to this side if there is a B or not. If there is no B, then that is a other loop. After all the A is already completed, that means we have to check only the B's. If there is no B, that means we reached our final state and our automata is accepted. Now for this example, suppose we have 2A, so first A is replaced by X, so we will go to this direction. First B should be replaced by Y. After that we have come up to this much, and our next iteration will start from A, this one. We will replace it by X and we will go to this side and we will replace it by Y. Now again when checking this side, when we came to X, now what we can see that there is no A left after X, so we have to check. But when we went this side, there is a B left, so this cannot be accepted because here number of B's are more, so this will be rejected. Similarly this one, 1A, 1B is checked, suppose X and Y. After that in the second iteration we will check 1A and 1B. So again we have crossed this. Now next one A, we have crossed it, so one B should be there. After that only we can go to like for next day, but there is no B, so there should be a halting in a non-final state. Similarly this one also should be a halting in a non-final state. Only in our first case we should halt in a final state. Now see in this example, suppose A and B n, same example if we take a to the power a and b. While designing, this designing is important because all the time we will be seeing like different types of examples. Suppose a and b and wcw or ww or any a to the power p or any other examples. All these things later we will see some example from the calculation part also, like 2 plus 3, what will be the output, that should be given by the Turing machine. So all these examples, if we don't solve it, if we don't know how to solve these problems or the logic behind this, then it will be a trouble for us. So see the diagram here. The initial state is q0. So what is our first work in the last example? What we have seen? First in q0, what we have to do? We have to change this a by some symbol, and then we have to go next stage. So we have changed this a by x here, and we are going to right hand side. Next q1, we have to, in q1 what we have to do? We have to ignore everything up to b. So in the first state what we have seen is we have got a, so a will be kept as it is, that is a. We are not replacing anything up to all the a, that is this a, then we got a b. Whenever we got a b, what we have to do? We have to replace it by y. So whenever we are doing any replace operation on any like something different, then we will change the basically state. So we are going to a new state. Similarly you can see here, after we have replaced a by x, so we are moving to q0 to q1. Now we have replaced b by y, so we are replacing this b by y, and we are going to new state q2. Now we are here q2. Now in q2 what we have to check is, we don't need to check this side, right? We have to go to this side. So once we go to this side, this is after b. When we was in q1 and b, on reading b we have written y, and we have moved to left hand side with q2. So this we have to remember, that we have done a left like LHS operation. Now what we have seen? We have seen here, what we are seeing here is a. So what do we have to do? We have to ignore all the a until we reach the first x. That means that all the these a's should be mapped later, but once we have to check now this a is replaced and this b is replaced. Now we will go to this a again, so that this iteration is completed. So we will ignore all the a, still we will be moving to right hand side. Once we see x, what we have to do? We will replace x by nothing, that is the same symbol it will be, and we will go to a, and we will just go to the q0 state. That you can imagine this, it is a for loop kind of thing, any loop structure, because all the time what we are doing, we are replacing a and b, we are checking one a corresponding b, we are checking, and then again we are coming back. So here we have done nothing actually. We have kept the x as it is, that is x replaced by x only, that is not no replacement, and we are moving to right, and we are reaching to q0. Now again in q0, now it will be locating a. So again same thing we have to do. We have replaced by x, and we are going to q1 state. In q1 state, first what we have seen? A. So we already have a transition, we don't need to write it. Next we have seen a b here also. Now a new symbol that we have encountered is b was replaced by y, and y was not written, but we have to go to up to this b. So we will be writing replacing this y to y, and we are going to right hand side. So that this transition we need to write here now. Now after b, checking in q1b, we have already a transition, that is q1b. We have already, b has to be replaced by y, and we have to go this side. That means this is our new state, that is q2. Now q2 is pointing to a y, but we don't have any transition here, so we will be writing a y here. So y is should not be replaced by anything, that is y is kept as it is, and we are moving to left hand side. Up to how much we have to look? We have to move to first that last replaced a, that is up to x. So we will be reaching again q0. So now we have to replace this and we have to replace this 2. Again when we are coming back, we are now in this x. After x we are getting a y here, that means no a's are left. So if we get a x after y, so what we have to do, we have to check for further y's. So in x what we have checked here is we have get a y after x. So finally on q0 if we get a y here, we will not get actually blank symbol. If we get a y here, we will not do anything, we will replace it by y. We will just keep it as it and we will go to right hand side. This is one possible move, so we will go to right hand side. So now we are going to a new state q3. In q3 what we can get, we can get more number of y's before our blank symbol. So all the y's is covered by this one, all the y's we have to check. Only after y, if we see a blank symbol, that is if we see a blank symbol and we have to replace, don't replace by anything and just go to R, and finally we will reach our final state. So this is the logic to read to check for this A equal to B or not. So same example is given with some like a same diagram is given with some example strings or W. Here an example is given AA BB. So first what we will do, in q0 we will replace it by x and we will go to q1, we will ignore first A, then we will go to B. So we have to remove this B by y, so we have removed it by B and we are going to left hand side q2. Now again we reach to q1 q2 x and finally again q0 y, q0 is pointing to A, again we will be replacing it by x and we will go to this side and finally this B will be replaced by y. We have to check up to this much and then there is no y left. Now we will go to YYR, finally we will go to if we have more number of y's, we will check all this y and finally we will go to blank symbol. So this is our corresponding diagram. Similarly, if we can solve a to the power n, b to the power n, then easily we can solve a to the power n, b to the power n, c to the power n. Like suppose we have now a, b, b and c, c. So what is the, if we apply the same logic, what we have to do, we at each iteration we will be replacing x, y, b by y as it is and c by a new symbol, that is now for the like simplicity we can say it as we have replaced it by z. Then we have to reach up to x. After that again same iteration x, y and z. After this we are like solving all the examples, then finally when we reach here up to x, that means no a's are left. Now we have to check whether any b's are left or not. After that we have to check whether any c's are left or not. Finally if we are in a blank symbol, that means this all the input are like as correct format, that is a to the power n, b to the power n and c to the power n, when it is accepted. If we find any other input other than this like a, b, b and c, then of course it should be rejected, because at certain it will be rejected in any intermediate state other than the final state. Now up to this is like some examples of Turing machine. So what we can say here is like what we have studied up to this is, in Turing machine we have seen from a state we read some input, we write it whether we are writing or not, like we write it at something there, whether we can write in the same symbol as it is or we replace it by a new symbol. Then we can go to any one direction, either left or right direction, and we reach to a new state. So we can what we can see is that this is the transition, that is on any input symbol what we have gone, where we have gone actually. Delta is like on q0 what we have done, we read a symbol on q0, what we do, we go to a new state q2, we are writing something on place of a, that is b, and we are going to right hand side. So this is a transition function for this one. Another transition we can see here, if we go to left direction, so if we go to left direction and our c is replaced by d and we are going to here left direction, so our q on reading on the state q1 what we have done, we have read the symbol c, we went to Q2 state and we are writing in place of C as D, and we are going to left hand side. So this is the transition function. So in short, transition function will be always like del function will be, we'll go to any state, we'll read some symbol from summation, actually suppose A for simplicity, then we'll go to another state and we'll write some another symbol from the summation or input head, then we'll go to either left or right direction. So this is our transition function for this one, for this Turing machine. So the formal definition for Turing machine is, Turing machine is represented by 7 tuple, that is q, summation, tau, del, q0, blank symbol and final state. From this we can identify all the states. Actually we already know what is q, that is the set of all the state. Then in this is input alphabet, tau is the all the symbol that you have written in that infinite tab, that is our tau symbol. Del is the transition function that we have just seen. Q0 is the initial state, F is the final state. We have seen here a new rule, that is from final state we cannot go to any other state, that is not allowed, that we have seen here. And one more symbol is blank symbol, that is our input are surrounded by some blank symbol in the tab, that we can imagine in this way. And this blank symbol can never be an element of our input string, that we have seen another like a rule. These are the two rules. And one more thing we have seen, that from a state, by reading a input we can go to only one state, not more than one state is allowed. Like if we go to by reading A, that is not allowed. Like for a particular input symbol you have to go to only only one state only. So this is our Turing machine's formal definition, that is Turing machine is correspondence of 7 tuple, where input symbol is a subset. We can imagine input symbol will be a part of our tau symbol. This is our tau symbol. So input, we are placing our input here, that means that input is always a subset of our tau symbol, and this blank symbol is a part of tau symbol, that we have to remember, but it is not a part of our input symbol. And q0 is an element of our states, and these are the initial state, and f is a pure subset of q. So now if we see any transition, here the input is C, A, B and A, and Q1 is pointing to B. So we can write, this is called instantaneous description. Again in Turing machine we can represent our machine by 3 things. One is instantaneous description, another one is transition table, and another one is transition diagram. So both, all these concepts actually you have already studied in PD or finite automata. Transition table we already know. Whenever we represent something in the form of a table, that our diagram or any all a set of transitions of or a particular table, then it is called transition table. And same thing can be represented by transition diagram, that is the state diagram. Whenever we are giving the state and transition in this form, that is our state diagram, and the same thing can be replaced as a table. And this is same thing can be also written as a instantaneous diagram, instantaneous description. What you can see here is like on Q2 is pointing to X and A, Y, B. So this is our input X, A, Y, B, and after this X is actually not replaced by anything here, and it is going to the next state, and here is Q0 and it is pointing to it, that is it moved to the right hand side. So X is here, after that Q0 will come and the remaining input will be here. So we can see this here, after that X and Y is here, so X, Y, and it is not replaced actually anything, and after that Q1 is pointing to B. So we can see here after X, Q1, Y, B, we have X, Y and Q1, B. So if we have many descriptions after one by one, like after this we are going to next, then we can write it directly by a star symbol. But again if we have in like different symbols, then basically it is not allowed. Specifically if you are given to solve an example, you cannot directly write that that initial state. After that you can directly placing a star and you are writing the final possible state, that is not allowed. You have to solve it throughout the with a proper example in this way, like after this state we are going to this and then this and this, in this way you have to write it. So this is the initial configuration of any Turing machine, that is on Q0. After Q0 we will be having the input string. So Q0 will always it will point our first input of the string, that is your if W is ABA, then it should always, this should be always Q0. It is here here W, it goes to this is the first transition and this is the last transition. This means that Q0 is the initial state and QF is our final state. So up to now what we have studied is Turing machine. If we consider our Turing machine is termed as we can say it in terms of state to alphabet, it is deterministic. By that is on Q0, by reading a input we can go to only one state only, not more than that is allowed. We have seen our input tab, other than like in LBA we have to have a fixed length of input tab, that is in LBA whatever the input symbol is, up to that is only our working part, that is it will be surrounded by some symbols, that is N marker, right and left hand marker, and this is only our tab, that is that finite length tab was there in LBA. But in Turing machine we can see that our tab symbol will be always followed by n number of symbols, those are called as blank symbol, and it is a infinite tab. And here you can keep any place, anywhere we can keep our input. Suppose we kept our then our initial state, whatever we generally determine it as Q0. So Q0 always points to our first input alphabet, and tab is also considered as input output file, like whatever we are giving the input. So this is the example of A and B and C N. So you can see here this transition, that is after A reading to like replaced by X, then Y, then B, and finally Z is replaced, and we are moving back to up to X. Then next iteration X is replaced, Y is replaced, and Z is again, C is replaced by Z, and here we got some new symbol, that is YN, A we have got here, and finally Y is like no symbols are there, so we reached from Q0 to Y, that is Q4, and finally Q5, and if all the inputs are equal, that means it is accepted. So these are the MCQs, some of the simple MCQs that you have to solve after this exam, this tutorial, and then finally these are some given terminal questions. So thank you for listening.